So for the first talk of this afternoon, we have two people from our secret Cambridge R&D lab, Justin and Rolf. So this secret R&D lab is the place where stuff like Docker for Mac and all the unikernels magic came to life. And now they are going to give us an update and also some internals about LinuxKit. LinuxKit, well, I think I shouldn't maybe spoil too much of the fun, otherwise they will have less to talk about. So please, one round of applause for Justin and Rolf, who will tell us all you need to know about LinuxKit.
Thanks for the introduction, Jerome. So we are going to do initially a small intro into LinuxKit. So what is LinuxKit? So LinuxKit is one of the Moby projects we announced at DockerCon in Austin, and it's a toolkit for building secure and portable operating systems which are lean, small, and they are optimized for containers. We have a tool called Moby, which we use to build system images, and for an operating system, it's everything we run on the operating system runs inside containers. And we have been using the containerd 1.0 branch for the last 4 months, so fairly early on, and we are really waiting for it to get released so that we can release LinuxKit as well. What we do with LinuxKit is we are building lightweight, fully customizable system images. To give you an overview of how that works, is we take a YAML file which describes the entire system which we want to build. We then have a tool called Moby, which takes the components specified in the YAML file and assembles it into images you can boot on hypervisors or even on bare metal. The Moby tool also verifies things like signatures of the packages which we use to assemble the final image. On the right-hand side, you see how the sort of end product will look like. We use very modern Linux kernels, so we typically track the latest stable releases of the Linux kernel. Our default kernel is always the latest long-term stable supported kernel, which is currently 4.9. On top of the kernel, there's a minimal init process, and all the init process is doing is it's basically starting containers using containerd. There are 3 types of containers which start. There are on-boot containers, which are executed when the system boots up, and you use them, for example, to set sysctl settings for the kernel, etc. Then, when the system is actually running, you typically just run service containers. The equivalent of them is something like daemons or other processes you would run in a normal Linux system. And we recently also introduced shutdown containers. So these are containers, if you shut down, then you can do some cleanup afterwards, like syncing your disk, your buffer cache to disk, etc. So as I said, we open sourced this in Austin about 6 months ago, and since then we got a lot of stars on GitHub. It seems very popular, but more importantly, over the last 6 months there have been over 1,400 commits to the repository. We have a very active community on a LinuxKit community Slack. Overall, the project has seen 80 individual contributors, but most importantly, there are 52 of them are external people, so not Docker employees. So I would like to, and I know that some of them are in the audience, I would like to give you a big thank you for your contributions. So what do all the 1,400 commits do? So since we open sourced it, so the major additions are we actually had added ARM64 support to LinuxKit, and that was largely done by an ARM employee called Dennis Chen, who was supposed to present on Thursday, but I think he couldn't make it. We also, if you recall from the DockerCon keynote demo, at the very end we demoed Kubernetes on LinuxKit, and as you may have seen in the keynote today, we have very much improved the Kubernetes support in LinuxKit, because the kube support, which is in LinuxKit, is actually the basis for Docker for Mac and Docker for Windows, the kube support in Docker for Mac and Docker for Windows. Another exciting thing which got added was support for Linux containers on Windows, which was also demoed at DockerCon in Austin, where Microsoft added a feature where you can run individual containers directly, Linux containers directly on Windows, and for that you need a very small customizable Linux system, and so we worked with them to build a minimal Linux system which then can be used with Linux containers on Windows. And there's actually a talk tomorrow by John Starks at, I think, 11 o'clock somewhere. So if you are interested in that, go and see it. When we open sourced it, we had support for running our LinuxKit images on things like HyperKit, Hyper-V, I think, and on Google Cloud. And since then, the area where probably a lot of external contributions came to were improve the platform support. So we can now have very easy booting of LinuxKit images on bare metal, on Packet.net, Azure and AWS, IBM Bluemix, VMware, Vultr, all these things got added mostly by the community. There also have been a whole bunch of small improvements to the system. As part of the ARM64 support, we had to rejig the whole packaging system. I'm going to talk about that a little bit later in more detail. We also changed the setup of the LinuxKit system to be fully immutable system images. We added a more flexible networking setup, and in particular, we added support for something called Wireguard. Justin is going to talk about that in a little while. That also required us to provide more flexible tools for sharing namespaces between system containers. We added better support for persistent disk support. Avi, who I just saw walking past, also added support for TPMs. And of course, we have been tracking the stable kernel. So we are currently on the 4.9 kernel, which is the latest long-term support kernel. And we tracked 4.10, 4.11, 4.12. Currently, the latest one is 4.13, and we are waiting for 4.14 to come out, which will be the next long-term support kernel. Now I'm going to give a short demo. Could you switch back to my laptop, please? That's actually working. Fantastic. But the font is a little bit too small for you, right? Let me increase this. So what we see here is we have two windows side by side. Is that better to read? Can you read? Okay. So we have two terminals. On the left-hand side, that's just on my local Mac. And on the right-hand side, I'm logged into an ARM64 server on Packet.net. And we're going to use a small demo file. Oh, I got locked out. Fantastic. This is not good. My network is gone. Maybe I should join DockerCon EU. Maybe it works now. Yay. I should go into the demo folder and let me. So what you see here is the YAML file I already mentioned before. And we have on both machines identical YAML files. So the YAML file specifies which kernel we want to boot. Here, then we have an init process, and the containerd version we want to use. Then there's a DHCP client, which gives us network connectivity. And finally, we specify a Getty container. As you can see, the hashes on the images we are using to build this are identical. But we are on two different architectures. So we can now do a Moby build of the demo file. Is my network going again? You can do that here as well. Network, please. It's there. This is painful. Okay. So what we now do is the Moby tool basically goes through the YAML file, looks at each packet, and is, if it's not already available in the local Docker store, we'll download it. It will verify the signature. You can see here that actually one of my certificates, which I used to sign the images, is about to expire. So we know this because the build actually is talking to the notary server, to the Docker Trusted Registry to verify the signatures, and it's a reminder to myself that I need to update my certificates. And you see it's basically running through the same process both on ARM and x86. Once the build is done, so you see that it's adding the containers to it. And on the ARM64 server here, which finished earlier, let me clear this. You see that it created a file for a kernel and the initial RAM disk, which contains all the containers, and the command line it should use when we execute it. So now that we have these, we can, let me adjust this slightly. We now have another command. We can do LinuxKit run of the demo. And this is now using KVM on ARM64 to build the LinuxKit image. And in the other window here, we do the same thing. And it's now booting the x86 image, which we built on HyperKit on my local Mac. Right? So to show you that we are in different architectures, we can look at the uname -m. So on the left-hand side, we are on x86 64. And on this side, we are on 64-bit ARM. So we use the same file, the same packages, and build it on different systems, and we got an x86 and an ARM64 image. Let me power these things off, if I can type. But if you look at the Moby tool itself, it has actually a bunch of alternative options to output images. So we can create images which we can boot on Google Cloud or Azure or AWS or on bare metal. But recently we also added an additional support here, which is this one here. So we can specify the output format. So if we do a Moby build here and specify the format, and we want to build for this thing here, we give the demo YAML. It will now take the same YAML file and it will produce a different image. And the image is targeted as a Raspberry Pi. And that's currently a PR. But I have a Raspberry Pi here with a LinuxKit sticker, of course. And I've already built this image and extracted it on this machine here. To show you the contents, it's basically the files needed to boot a Raspberry Pi. So we booted via U-boot. There's a kernel image in U-boot format, an init read here, and the device tree file, which describes the hardware. So the build is still going on, but we can probably boot this up. I have it connected via a serial console here, and you can see on the left-hand side the output of the serial console. So I'm now plugging it into power, and you see that U-boot is basically loading. It's loading the kernel file and the initial RAM disk. And now it's starting the kernel, and you should soon, hopefully, see that the kernel boots up. So we now just booted the build on the right-hand side here is not quite finished, but we can just copy the contents of the tar file onto a flash, put it in here, boot it, and you're done. So basically, you can build fully customizable images to run on your Raspberry Pi, on your infrastructure, on bare metal, wherever you like. So that's the end of the demo. Could we switch back to... Thank you. Right, how does this all work? So we use the same packages, the same base file to build images for both x86 and ARM64. LinuxKit packages are basically small container images which we store on hub. They're pulled and assembled using the Mobi tool, as you saw. They are signed with Notary, but the key thing is that these images are multi-arch images. Let's have a look at the DHCP package which we used earlier. So packages are built using a Docker file, and so all the core LinuxKit packages are actually built from what we call the Alpine base image, which you see where the green arrow is. So the LinuxKit base image is essentially a APK mirror. So APK is the Alpine Linux packaging system. So it's a mirror of all the Alpine packages you need to build our LinuxKit packages. Right? So it contains the C compiler we use to compile the kernel. It contains the Go compiler we use to compile various Go binaries, which we use in LinuxKit. And of course, it contains packages like the DHCP client package. So when we build this base image, we record the exact version of all the packages which we put into this mirror image, right? And then we push this base image to Docker Hub. It is signed. And now we can build other packages, like actual LinuxKit packages from it. But because we have mirrored all the Alpine packages we need and the tool chain and everything else in this one image, it allows us to then, when we build LinuxKit images, to basically build them without network. So it's not that the Docker file is pulling in some random version of some random piece of software from the network into your package, but you know exactly which packages you have available, which versions. And what that gives us is we can basically do repeatable builds. So we have the base image, we know exactly which base image we use, we have all the versions recorded, and so whenever we rebuild a package, we know exactly we get the same package. I'm deliberately not saying that it's reproducible builds, because that typically requires that all your timestamps are identical as well, which is a little bit harder to do, but we have the same input. The same inputs will always give us the same output in packages, so they are repeatable builds. The other feature which we use, so the base image is quite large, it's about 200 or 300 megabytes, which is actually quite small considering that it has like C compilers, Go compilers, and various other things in there. And then we use a feature which was introduced in Docker 1705, which is called multi-stage build. So if you have a look at this Docker file, you see that there are actually two from lines. So there's a from line which pulls in the Alpine base image, and then there is the second stage which we actually use to package up our package, and that starts from scratch, so it's an empty container. What we then do is, in the first stage, we basically use the APK mirror of the packages, and we install just the packages we want. In this case, it's BusyBox, DHCP, the DHCP client daemon, which is a little bit odd, and Muzzle, which is the lightweight C library. But instead of installing it in the container, we actually install it in a subdirectory in /out here. And then in the second stage, we copy from the previous stage just the contents of /out into the root file system of the package, right? We then add additional files like the DHCP configuration, for example. What this gives us is, although we have a relatively big, like 200-300 megabyte base image, we can make our packages, like in this case, the Dhcpcd package, really small. So it's just 2 megabytes in size, and it contains just the DHCP daemon, the client daemon, the configuration file, and BusyBox, and that's it. Right, and to a large extent, the size is so small because in Alpine, the packages, people really care about building small, tiny packages, and we are thankful for being able to reuse these small packages. So, excuse me. The next thing then is, for a given LinuxKit package, you can specify a default command to be executed when the container starts up. And in this case, we start the DHCP client with the configuration. You can overwrite these entry points using the YAML file which we used to build the image. Finally, there's this slightly long and complicated line here. We also store with the package a default configuration for the container, so that they are basically OCI runtime configuration snippets. So if you want to run a DHCP client inside a container to set the IP address of an interface, it needs to have certain extended capabilities. So it needs to, for example, have the netadmin capability. It needs to be able to bind to a network interface. It needs to have sysadmin capability. So instead of specifying these details in every YAML file you're doing, we are basically putting default snippets of these things, which are essential to run it, inside a label on a container image. And the Moby tool will look at that label, and if the values which are in the label are not specified explicitly in the YAML file, we'll take them from the label and use them as default values. And that way the YAML files become a lot more readable. So that was an addition which we added maybe like a few weeks after DockerCon, because the YAML files got really unreadable. So with the Docker file, we now want to build the package, right? So we obviously do a normal Docker build first, but there are a few things here which are worth paying attention to. So first of all, we add additional labels to the package. One label basically says which source code repository it was built from. The other label says which Git commit it was built from. That allows us later, when we pull an image, inspect an image, we can find the source code for it. From the source code, we can find out which Alpine base it was built from, and from that we know which versions of which software it was built from. So we have the whole chain of versions basically coded into the packages. The other interesting thing, which you may have observed in the YAML files, we all have a fairly long hash at the end as a tag of the package, right? So what we use to tag packages is the content hash, or the hash of all the source files used to build the package. So for the DHCP package which we are looking at, it would be the hash of the Docker file and the hash of the make file, if there is a make file, and the DHCP configuration file which we use. So that gives us a hash. We actually use a Git tree hash, which is very easy to use. You just say, give us the content hash of this directory, thank you. We also tag, excuse me, we also tag the images with the architecture. And we come to that in a little bit, what that means. So then we push it to hub, and we always push with Docker Content Trust enabled, which means that if I push it, I have to sign it with my key. If Justin pushes it, he has to sign it with his key. But it means that we can then later verify the contents of that package. There's actually a lot more to this, and there's a blog post on the Moby project, which is called Sign All the Things. So if you're interested in that particular aspect of LinuxKit, have a read. It's very interesting. So now the interesting part, the multi-arch build. So we pushed in this case, the AMD 64 image to hub. We've pushed the same image, which has the same content hashed on an ARM64 system, to hub, but with the AR64 or ARM64 extension. And currently we are using a tool called the Manifest tool, which Phil Estes wrote, who is actually giving a presentation on multi-arch images at the same time as this talk. So maybe you should check out the recording of that if you're interested in it. But what this basically does is, it says we are having a template. We're using a template, which is the hash plus the architecture, and we push that to Docker Hub without the architecture suffix, right? And what this does is pushing, instead of pushing an image, it's pushing a manifest list. The manifest list says, if you pull this particular image on an AMD 64 system, you will get this other image from Hub, which is the one with a -AMD 64. If you pull it from an ARM 64 system, it will pull the ARM 64. right? So and with that, we can basically, with this particular step, we can basically use a YAML file which has identical package versions and hashes in there, and we can build it both on x86 and ARM. The final step here is that we then take the manifest list which we push to hub, and we also sign it with notary. That means if you then pull it, the initial pull of the manifest list, we can verify the contents of it. We then also verify the contents or the signatures when we pull the actual architecture-specific image. Now, the last two steps are quite intricate and long command line invocations, but hopefully this soon will be a lot easier because there is a PR out there for the Docker CLI called Docker Manifest, which will make it much easier to work with the manifest lists. And there are also PRs out there to integrate some of the notary functionality into Docker itself, and that will be available as Docker Trust. So in summary, we build packages from a base image with Docker files. We build packages, use YAML file to get a system image. I'm now handing over to Justin.
So I'm going to talk about some of the things you can do because the great thing about LinuxKit is built on Containerd and on runc, the OCI and the OCI standards, and you can do loads of things that those give to you. And a while ago, we needed to integrate Wireguard into LinuxKit, and Wireguard's a really, really cool, fast, modern, secure VPN that we're now shipping with the kernels, all the LinuxKit kernels, because it's really useful. It's being upstreamed into Linux, hopefully over the next few months. The integration work's going on at the moment. And it's really quite cool because it just appears as a network interface, but everything that goes down that interface is automatically encrypted. And so we needed to come up with a way that made it really easy to use this in LinuxKit, so you could try this out and build tunnels and things like that. So we added the whole facility to be able to create and share namespaces between the services that you're running in LinuxKit. So each container, rather than running isolated in its own namespaces, like the first version, they could be shared in common namespaces. In particular, you could create a network interface, move some interfaces into it, and just select that you want to use that for your system container. So I'm going to show you a little example of how this works. I'm going to build two LinuxKit VMs, one of which I'm going to run on my laptop, one of which is running Redis, which doesn't have any encryption or authentication on its interface, and I'm going to connect to it from another one but I'm going to run everything over a VPN tunnel so it's all secure. In the YAML file, the files are all in the repo and the examples, but you can see what I do is on at boot time, I set up a new namespace called WG0 for Wireguard, and I say I want a new network namespace here, and I want to create the Wireguard interface and move it inside this new namespace, and then I want to bind this namespace into the file system here, and then when I run Redis, I'll tell it I want to use the network namespace that I created earlier. When it runs Redis, and you can run multiple interfaces here. So if we actually look at what this looks like when you're actually running it, I've got two machines. I've started one of them up already. This is the machine that's running the Redis server. And if you look at its interface config, it's on 192.165.3, and somewhere in there's Redis server running here, and then I can boot up the second half of the config, which is the one where I'm just going to run a login container, which happens to have the Redis CLI in, again, inside this namespace. So if I run this one, boot up our LinuxKit machine, always nice and quick, like working with LinuxKit is. I'm now inside this container, and as you can see, there's just this Wireguard interface here, and if I now run, clear, we can run the Redis CLI, and we want to point it at 192.168.2.1, which is the other end of our tunnel, and we can run a Redis command info, and we've connected over it, all encrypted. All the traffic is going between these two VMs here that are running separately, as separate VMs on my Mac. So it's really, really straightforward that you can really create really quite sophisticated setups with different namespaces and so on. And you can share namespaces between system containers, and you can use tools like Wireguard to set up really easy VPNs between them and so on. So it's a really powerful and easy to use way of basically using all the tools that the OCI toolbox gives you with namespaces, and Linux gives you with namespaces to do really interesting system things with system containers. I'm also going to talk to you very briefly about building Kubernetes, which we built for Docker for Mac in particular, but also for other uses. So we've been working on this since before the last DockerCon, particularly with the help of Ilya from Weave, who's worked with us. And we've been really working towards making this production ready so that we can ship it now in the next Docker for Mac, and also we can use it in production deployments as well in future as well. So for Docker for AWS and other platforms, and you can all use it yourself for your own use cases with Kubernetes. We've got a lot of interest in people using LinuxKit for Kubernetes deployments as well. So we're really hoping to get towards production deployments with replicated etcd. There's talk about this on the Maybe Summit on Thursday as well. In brief, we built the setup with LinuxKit on kubeadm, which is a nice tool for installing and configuring Kube, which we found really nice. We run the kubelet in a system container, but it's a kind of complicated setup, as I'll show you in a minute. It shares lots of the file system. It's all immutable infrastructure like LinuxKit provides, and we do support multiple nodes. The desktop demo at the moment is a single node, but with Linux, if you use the LinuxKit examples in the repo, you can set up multiple node clusters on the desktop as well, and we may ship that in a future Docker desktop. So I'm going to show you how it's all put together. I haven't got that much time, so it's going to be brief, but do come and talk to us later if you want to see it in more detail. And also, there's people who can demo it down at... no, I don't want to answer your phone call. There's people who can demo it on the booth downstairs, the Moby booth downstairs. So this is basically the YAML file for the Kubernetes. Is kind of quite complicated, but most of it's actually just standard LinuxKit stuff for mounting disks, DHCP, things like that. There's the kubelet image, which we're running, which I'll show you in a second. And then we're running Docker. We also have it running just with CRI containerd, which is how it's going to be shipped in future, because that's when using the CRI with that, which is really great as well. As you can see, there's a lot of complicated sharing going on, which I'm not going to go into a lot of detail, but basically Kube needs to share things like the CNI, the networking setup, the kubelet plugins, and so on, so that Docker needs to see these so it can start up. It can start up kubelet plugins, it can start up the networking and things like that. And then we've got some config files, a nice thing saying, so the OS project, and the network YAML for setting up the network. We're using Weave, but you can use other network plugins with this. It's totally configurable. Then here's the Docker file for the kubelet itself. As you can see, you can configure the Kubernetes version. We can upgrade to 1.8.1 now, CNI version. And we check out Kubernetes and we build the kubelet, kubectl, and kubeadm. So it's a standard build of those from source. And then we add the package we need at runtime, and we run this kubelet shell script here, which is this script here, which basically does the it works out if this has ever run before we're on first boot. If we're on first boot, it runs kubeadm to configure the cluster. It then touches the files so that we know we've run it before, and if we can read the user data from the cluster, if we've got a metadata config in order to do multi-node and join, we can join an existing cluster from user data. So we can configure in AWS metadata that we want to join a particular cluster when this node boots up, and it'll do that join automatically, which is makes doing multi-node clusters really easy. And then there's some comments about race conditions, which we need to fix. We're not quite production ready yet. And then we start the kubelet. And then we start the kubelet. So that's really the kind of overall kind of structure. You get a feel for how these YAML files put together and what's actually going on. There's a lot of detail and things to get right, but fundamentally it's quite understandable. It's composed out of normal open source tools. This is all open source, this is all in the LinuxKit repo. You can try it out yourself, configure it yourself, change it, make it work, do whatever you want to do, customize it in any way you want, and contribute improvements back. There's a load more talks around this, as Rolf mentioned. So immediately after this, Tycho is doing a talk about upstream kernel developments, which is really interesting. The multi-arch talk was at the same time as this, so you missed it, but it will be on video. John's talk tomorrow, Linux Containers on Windows, is going to be really interesting. Nathaniel is talking about Alpine Linux, which is the base we use to build everything, at lunchtime. Qualcomm have a booth in the exhibit hall showing LinuxKit on ARM64, which is really cool. We didn't know they were going to do this. And on Thursday, if you come to the Maybe Summit, we've got loads of talks about LinuxKit. Andrew is talking about LinuxKit on ARM. Sven is talking about Rancher OS and LinuxKit. Stephen and Phil are talking about Containerd. There's actually more things as well. There's actually there's an InfraKit and LinuxKit talk from IBM as well. So there's like all sorts of things, and you can come and talk about stuff there as well. I reckon we've got time for like one question, maybe. Or maybe two of you ask them really fast.
Yeah. Technical difficulties created a little bit.
So may I go ahead?
Sure.
All right. So may we understand that LinuxKit is some kind of unikernel that runs multiple Docker processes inside it?
It's not. No, it's not a unikernel. It shares some of the same characteristics in terms of immutability and kind of being a special purpose thing rather than general purpose thing, but it's not actually a unikernel. It's a normal Linux distro, and you can understand it with your normal Linux distro tools and debugging. You know, it really is just presenting kernel and user space set up to run containers.
Are you going to support building Kubernetes images for nodes and masters?
You can. Yeah, there's some demos of multi-master kube on running configured with InfraKit on Thursday, but it's at the moment we're using kubeadm, so which doesn't support clustered etcd, but we are looking at ways to. So the InfraKit build basically builds its own etcd cluster by hand and kind of connects it to that. But we're just working on getting the details done on that, because we obviously want it to be fully production quality for not just desktop use cases.
Thank you.
I think we're out of time.
Yep.
Okay, if you have more questions, they will be available
around.
anyway. Yeah. Thanks, everyone. One more round of applause for Rolf and Justin.
Sorry, it was a bit late.
That's okay.
Yeah.